Friends, in the earlier video of this series, we learned about frictional electricity, charges, how are they developed, and quantization of charge. Friends, if you haven't watched that particular video, you can click on the right hand corner of this particular video and go and watch that particular video. In this particular video, we are going to discuss about Coulomb's law. Coulomb's law states that the magnitude of force of attraction or repulsion between any 2 point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. And this force always going to act along the line joining the two charges. Friends, if you remember, in our earlier video, we discussed about one particular property of charges, that like charges were repelling each other and unlike charges were attracting each other. The magnitude of attraction or repulsion is in fact going to define by this particular law, which is called as Coulomb's law. And the Coulomb's law is basically talking about the magnitude of the charge, friends. So you should remember, it talks about the magnitude and not the direction. And what does it say? It says that the magnitude of the force is directly proportional to the product of the magnitude of the charges. That means you just be simply taking the magnitude and not the positive or the negative sign. You should be concentrated, or you should be looking focused towards the magnitude 5 microcoulomb and 1 microcoulomb. So you should be talking about 5 microcoulomb and 1 microcoulomb, rather being concerned about what the sign or what the nature of the charge is. The second most important aspect is that you should understand in Coulomb's law that Coulomb's law is applicable only for two. That means a pair of point and stationary charges. So pair, it acts between a pair of charges, and the charges should be of point. That the dimension of the charged body should be very, very small in comparison to the distance between the two charges. Friends, if the body is not a point charge, then the Coulomb's law cannot be applied. We need to develop some other mechanism, some other laws in order to find out the force between the two charges. And that we will be learning in Gauss law, friends. So as I told you, this law is applicable for point charges. So the size of the charge has to be very small in comparison to the distances between the two charges, friends. So here you can see these are the 2 point charges that I have denoted, and the distance between them happens to be r. This distance is going to be taken from the center of the two charged bodies. And then the Coulomb's law is going to talk about that the force between these two charges will be directly proportional to the magnitude. So we are not interested into the sign or the nature of the two charges. The force is directly proportional to the magnitude of the two charges, and it is inversely proportional to the square of the distance. So if the distance between them happens to be r, then it is inversely proportional to the magnitude of the force is inversely proportional to this square of the distance between the two. Combining them together, I will be getting this particular thing, F being proportional to Q1 Q2 upon R square, and bringing the proportionality constant, F is equals to C Q1 Q2 by R square. This proportionality constant C depends upon the nature of the medium between the two charges, or the nature of the medium in which these two charges are placed, and it also depends upon the system of unit you are using it. Whether you are using a CGS system of unit, whether you are using an SI system of unit, it definitely going to depend upon that thing, and that makes this proportionality constant C is not to be a universal constant. The magnitude of C happens to be 9 into 10 to the power of 9 in SI system of unit. And friends, this C is equal to 1 upon 4 pi epsilon naught where epsilon naught is referred as absolute permittivity or permittivity of free space or vacuum. Now permittivity has got a value of 8.854 into 10 to the power of minus 12 SI unit in SI system of unit. Now friends, what is permittivity? We will discuss it in much more greater detail in my further coming video. Presently at this juncture you should be aware of the fact that C is 1 upon 4 pi epsilon naught for vacuum or free space. Friends, in SI system of unit, charges are always measured in Coulomb and forces in Newton and distances in meter, and if you can substitute all those things in C being equal to 1 upon 4 pi epsilon naught, you get the SI unit for epsilon naught, which happens to be Coulomb square per Newton per meter square. What I would like you all to do presently, you should pause this particular video at this juncture and try to do a little bit of mathematics and find out the dimensions of absolute permittivity. That is, you are going to substitute the dimensions for Coulomb, you are going to substitute the dimensions for Newton, you are going to use the dimensions for meter and try to bring out an answer for me for epsilon naught. Once you have done, you can check the dimensional formula that I have particularly derived. You can also take the opportunity to find out or to express epsilon naught in fundamentals unit. So try it out. What are the fundamental units? They happens to be kilogram, meter, seconds, ampere. So those fundamental quantities that you studied in class 11, when any quantity is expressed in units of those fundamental quantities, we call it as to be expressed in fundamental quantities. So when I am going to express epsilon naught in fundamental quantities, the answer should come out as per kg per meter cube second to the power of 4 ampere to the power of 2. So what I have done, I have used the dimensional formula to express epsilon naught in terms of fundamental units, friends. Why I have taken this as a part of my discussion? Because the council, the ISC board, often ask you either to state the dimensional formula of absolute permittivity, or it may also go and ask you to express absolute permittivity in terms of fundamental units. So this becomes a very important question for you all at class 12th level, friends. Now for any other medium apart from vacuum or free space, that particular constant C would be written as 1 upon 4 pi epsilon. Friends, epsilon, now if you notice over here, epsilon, this is referred as permittivity. So epsilon naught was the absolute permittivity, whereas epsilon is called as simply as permittivity of any particular medium, and this permittivity is also referred as electric conductive capacity. And what it does, it measures the ability of a medium to store electrostatic potential energy. So by knowing epsilon or epsilon naught, you are able to measure how much a particular medium can hold the charge in form of electrostatic potential energy. Electrical conducting mediums such as let's say as conductors would have higher value of permittivity, whereas insulating medium would have a very lower value of permittivity. And if it is a perfect insulator, it will have a value of 0, and if it is a perfect conductor, it will have a permittivity having a value of infinitely large. So you can't have an epsilon for any medium less than 0 because it can't hold any charge, or it doesn't have any ability to hold the charge, and for a perfectly conducting medium it will be having very large quantity of epsilon. Thus combining the value of C or putting the value of C in the expression for our Coulomb's law, we will get the Coulomb's law to be stated in two different formats. The first one is for free space or vacuum. The Coulomb's law can be stated as 1 upon 4 pi epsilon naught q1 q2 by r square, whereas for in any other medium the Coulomb's law can be stated as F is equals to 1 upon 4 pi epsilon q1 q2 by r square. Now please pay attention over here. The epsilon naught over here in this particular expression is called as absolute permittivity or permittivity of free space or vacuum, whereas here it is epsilon, which is known as permittivity of any medium. As I just now discussed, what does the permittivity means? It's the charge holding capacity in very simplest format, if you can put that thing into your mind. Now if I compare the permittivity of any medium with the permittivity of vacuum, or with the permittivity of free space, that or simply the absolute permittivity, you can see over here. And what I'm doing, I'm comparing the permittivity of the medium with the absolute permittivity. This particular ratio that you are going to get is going to be referred as dielectric constant K. So I can replace epsilon, or simply doing some small amount of mathematics, I'm bringing this over there. I can get epsilon as K times epsilon naught, and then I'm going to put it this particular value over here in this particular expression, and what I'm going to get, I can get a generalized form of a Coulomb's law. F is equals to 1 upon 4 pi K times of epsilon naught q1 q2 by r square. What does K? Where the K stands for dielectric constant. Now this is the scalar form of Coulomb's law. As you can see over here, it does not tell me any direction format. In the vector form of the Coulomb's law, I'm going to use the unit vector. Remember, unit vectors are always used when the vectors happens to lie in the same plane. So force vector will be equals to 1 upon 4 pi epsilon naught q1 q2 by r square, and unit vector r. Friends, I'm not using the 1-2 format over here because the council has already stated that it need not to be told at this juncture. So that's the reason why I've just avoided over at this particular point. So you can use Coulomb's law's vector form simply as a F vector is equals to 1 upon 4 pi epsilon naught q1 q2 by r square and a unit vector r. One should always remember that Coulomb's law is an example of a central force. So as when I say the Coulomb's law is an example of a central force, what does exactly I mean? So suppose I have got two charges. Let me put this as the first charge A, and let me say this as the second charge B. Now this is the line which joins the two charges. Let me say this is of plus q coulomb and this happens to be minus of q2 coulomb. Now q1 and q2 are going to be attracting each other because they are unlike charges, and the force of attraction will act along the line. So this is the line which joins the two charges. So the force of attraction, q2 pulls q1 towards itself, and this force of attraction is going to act along the line which happens to join the two charges. Similarly, q2 will be experiencing a pulling force due to q1, and this force is going to act along the line joining the two charges. So that is what I mean when I say the central force. Now you should remember, when I'm talking about the central force, the force can't act in any other direction. It can't be a pulling force like this. This is not possible. It can't be a pulling force like this. So the pulling force is always going to act along the line that is going to join the two charges. Suppose if I draw one charge over here, let me say q1, let's call it as a charge, and another charge B over here, let's say q2 charge. Both charges are positive in nature, so the line which joins the two charge happens to be like this. Then they will repel, push each other. So the pushing force will act along the line joining the two charges. So whenever the force acts along the line joining the two charges, that's what is called as an example of central force. So this is why we often prefer to call these forces as an example of central forces. This is not possible. Okay, friends. So one should remember that Coulomb's force is an example of a central force. Coming back to our discussion point, what are the properties associated with the Coulomb's law? The first property is that since the Coulomb's law has got r square factor in the denominator, that's why it is always referred as inverse square law. As I just now told you, it's an example of a central force. That simply means the force of attraction or repulsion will act along the line joining the two charges. So the negative charge is pulling the positive charge, so it is acting along the line which joins the two charges. So here you can see this is acting along the line which is joining the two charges. Similarly, the positive charge also pulls the negative charge, and so it attracts this negative charge, and this force of attraction due to the positive charge also acts along the line joining the two charges. So you can see that it's acting along the line joining the two charges. Next property talks about that these forces are an example of action and reaction pair. That means the magnitude of the force by which the negative charge pulls. So let me call this charge as A while this charge as B. So the pulling force of B on A or the pulling force of A on B, both of these forces will be equal in magnitude. Okay, so they are equal in magnitude, but the direction, so this force acts along positive x-axis, so I'm putting as I cap, whereas if you notice over here, this force acts opposite or to the negative of the x-axis, so I would put as minus Fi cap. So both the forces are equal in magnitude, but they are oppositely directed. So that makes the forces to be referred as action-reaction pair. So both the forces are equal in magnitude, that is F1 is being equal to F2, F that B puts on A is equal to F that A puts on B. Both the forces are equal in magnitude, but their direction happens to be opposite to each other. So friends, that's what I mean when I say the forces forms an action-reaction pair. As I told you, like charges repel each other, whereas unlike charges attract each other. So like forces are always going to be pushing forces, whereas unlike forces or unlike charges are going to pull each other. So you can think in that term. So they would push and drive them apart. So if they are positive charges or even if they are negative charges, they will push each other apart, but if there is a positive and a negative charge, they will pull each other and bring them closer. Remember, once again I would like to re-emphasize, these forces would always act along the line joining the two charges. That means if one charge would have been here, another charge would have been here. So if they would have been the like charges and they would have been they are going to push each other, so the one positive charge would be driven in this particular direction and the other positive charge would be driven in this particular direction. Similarly, if there would have been a positive charge over here, another negative charge over here, so this is the line which join the two charges, so they will be pulling each other. So the positive would have pulled towards the negative charge, whereas the negative charge must have been pulled along the line joining the two charges. So friends, do remember of the fact that these forces are an example of central force. And Coulomb's law is an example of action at a distance. That means it does not require a mechanical contact between the two charges to experience this force. That also means that this force will be manifested with the help of the fields. For example, gravitational force. Gravitational force is also an example of action at distance. Gravitational pull does not require the mechanical contact to be there. Similarly, electrostatic force also do not require this particular contact. It can act from a distance. So friends, if you start comparing with the gravitational force that you studied in your junior classes, in your class 11th, you might remember that it was also an example of a central force. It was acting along the line joining the two charges. It was also an example of action at a distance. It was also an inverse square law. It was following an inverse square law. So all these points are the points of similarity. The first one, both the forces, whether Coulombian, whether gravitational, both are example of inverse square law of force. Both are example of central force. Both, that means both the forces acts along the line joining the two charges, and both forces manifest themselves in the form of fields. That means they are acting from a distance. So that's why we are going to call them action at a distance. So both manifest themselves in the form of field. The gravitational force acts in the with the help of a gravitational field. Electrostatic force acts with the help of electric field, and we are going to discuss electric field in much more greater details in the coming days, friends. Now, as I told you, it follows the inverse square law. So if I plot a graph between F and R, F against R, so on the y-axis I plot force and on the x-axis I plot distance, then the curve between force and distance happens to be a rectangular hyperbola. So you can see this particular curve will be a rectangular hyperbola. Now, this is a very important curve. Take care about these curves that you are going to study. Most of the time in boards you will be asked to draw the curve, different curves, and the marking scheme for drawing the graph is being there it's divided into 2 marks. Every graph that you get in boards is generally for 2 marks. So the first marks is awarded for the correct shape. That means the shape of the graph should be correct. That means if it is a rectangular hyperbola, it should represent the rectangular hyperbola. And the second marks is for drawing the correct labeled axis. Correctly labeled axis. So friends, whenever you have been asked to draw the graphs, remember it will be for 2 marks. 1 marks for the shape, correct shape, 1 marks for the correctly labeled axis. So remember, whenever you are labeling, label the axis along with the units. Don't forget to mention the units. So here I am plotting the distance, here I am plotting the force. So what is the SI unit for force? In Newton and meter. So this was all as far as the properties of the Coulomb's law were concerned. Let's move on to the next important part, and that is the principle of superposition, friends. Remember, Coulomb's law was talking about a pair of charges. That means it discussed about the forces that was existing between the 2 point particle charges. Now, what would happen if I have got n number of charges or collection of charges? Then how I'm going to find out the forces? And in that situation, I come to principle of superposition. What does the principle of superposition is talking about? It talks about when there are a number of charges interacting with each other, then the total force on any one particular charge happens to be the vector sum of all the individual forces that particular charge experiences due to the other charges. And we are going to follow the vector law of addition, because the force being a vector quantity, I am going to follow the law of vector addition. And these forces does not get affected by the presence of other charges. So let's begin. You can see there are certain charges over here. This is the charge Q1, followed by charges Q2, Q3, Q4, and so on. So friends, how these forces are going to act? Let me draw those forces also. So this is a force, this is the charge on which I am interested in finding out the net force. So I have highlighted this particular force Q1, okay. So here on this particular charge I am interested in finding out the force. So what I do, I try to find out the forces that are going to be experienced by Q1 due to the other of the charges in the vicinity. So Q1, and I am taking the charge Q2. I have drawn the centers of both the charges. Remember, Coulomb's law is a central force. And what type of charges are we dealing with, Q1 and Q2? They happens to be unlike charges. So Q2 will pull Q1 towards itself, and the force that Q2 applies on Q1, I am labeling it as F1. Similarly, due to Q3, once again I join the center of the two charges, and again just see what nature of the charges they are. They are like natured, so the Q3 will push Q1 away, and this pushing force is going to act along the line joining the two charges, and let me call that as F2. Now what about Q4? Let's join the center of both the charges. Again, they are unlike natured. What unlike nature forces are? They are attractive forces. Q4 is going to pull Q1, and this particular force once again will act along the line joining the two charges. Let's call it as F3. Now I got another force, Q5. What natured? like natured, it's going to push Q1 away, and let's call that force as F4. Then I've got another pair, Q6, like unlike paired. What type of force is going to exert? Attractive, and this particular force is also going to act along the line and joining the two, pulling it towards itself, and that's, we call it as F5. So friends, there are 5 particular forces: F1, F2, F3, F4 and F5. So what I did, I find out the net force. I found out the forces existing between each pair, taking Q1 because I was interested in Q1. So I took Q1, okay, I took this particular charge and then I took one pair. Find that force. The magnitude of this force definitely will be given by 1 by 4 pi epsilon naught Q1 Q2 by whatsoever the distance. Let me call this distance as R1 square. Then I took F2, found out F2. In this particular case, F2 will be 1 upon 4 pi epsilon naught Q1 Q3 upon whatsoever the distance. Let's call this distance as R2, this distance as R1, this distance as R3, and so on. This as R4, this as R5, and I will find out individual forces F1, F2, F3. So F1 will then be, the magnitude of F1 will be 1 upon 4 pi epsilon naught Q1 Q2 upon R1 square. Then F2 being equal to 1 upon 4 pi epsilon naught Q1 Q3 upon R2 square. Similarly, I can find out F3, 1 upon 4 pi epsilon naught, once again Q1 Q4 upon R3 square, and so on, friends. Once I found out these individual forces, what I'm going to do, then I'm going to use the vector law of addition in order to find out the net resultant force, friends. Now, that's what is the principle of superposition talks. It talks about to find out the individual forces between the pair of each charges, assuming that the other charges are absent, and then in order to find out the net force, we should use the vector sum in order to get the resultant force. So the net force will then be the vector sum, friends. So this was about the principle of superposition, friends. Numerous number of numerical problems will be based on to this. Whenever you go back to your textbook, please solve them out. They are going to be of immense use for you all for the next chapter to follow up. If you are still not aware about the vector law of addition, so you can go back to my vector classes or vector addition slides and refer to that. A small part of it I'm just illustrating over here. The net force between any two vector quantities is given by the formula F net is equals to under the root of F1 square plus F2 square plus 2F1 F2 cos theta, and the angle between the two vector and the angle between the resultant and the first vector is given by the formula tan phi is equals to F2 sin theta upon F1 plus F2 cos theta. Here I'm illustrating it. You can see I've got F1 force over here, F2 force over here, and the angle between both the forces happens to be theta. Then the resultant of this force is given by the formula under the root of F1 square plus F2 square plus 2F1 F2 cos theta, and the resultant will make the angle phi. So this is the net resultant force and the angle that it makes with the first vector. Remember, I'm talking about the angle that it makes with the first vector. So this is my first vector. You can see over here. So the angle that this resultant vector is making with the first vector is phi, and the value of tan phi can then be calculated with the help of formula F2 sin theta upon F1 plus F2 cos theta, friends. Now, if theta has got different values, I'm just summarizing those results for different values. You can use the same in any numerical formula. It is going to be of great help to you. One very important part of the result is if both the forces are equal in magnitude. That means if F1 and F2 are equal in magnitude, then the resultant vector, this F net, is always going to lie along the angle bisector. So remember, friends, it lies somewhere in between, but if both the forces are equal in magnitude, then this resultant will be lying exactly at angular bisector. So in that situation, phi will be equals to theta by 2. but this is one particular case in which this is going to happen. So this result from vector addition will definitely be of very use to you when you are going to solve numerical problems, friends. Start solving the numerical problems from the chapter first from the Newton physics, or from any other textbook that have been there with you all. And if you get any numerical problems as a problem for you, just put down into the comment of this particular video, and I will come back to the solution of that particular video. In fact, I have loaded number of solutions from Newton physics. You can once again click onto the top right hand corner to see those solutions that have been mentioned in the YouTube, friends. Friends, with the help of Coulomb's law, we can define the SI unit of charge. Remember, I am defining the SI unit of charge. So this particular formula that we got from the Coulomb's law can be utilized to define the 1 Coulomb. So if I take Q1 and Q2 to be equal to 1 Coulomb and distance R to be equal to 1 meter, then F being equal to 9 into 10 to the power of 9, and this particular definition can then be used to defining 1 Coulomb. 1 Coulomb is that charge which will repel an equal and opposite similar charge with a force of 9 into 10 to the power of 9 when placed in vacuum or air at a distance of 1 meter from each other. Friends, please remember the lines that I have highlighted becomes a very important for definition. So this definition once again can be asked in your board examination for 1 marks. So take care about this particular definition, which is important for 1 mark. Friends, thank you for watching. Don't forget to give a like or comment. अगर अभी तक आपने मेरे इस चैनल को सब्सक्राइब नहीं किया है तो please do the same. Don't forget to hit the bell icon so that whenever a new video is loaded, you get the notification. Take care, and we will meet back again with a new video and a new solution. Thank you, friends.